So in Calc 1, when you first get to the definition or concept of derivative, they describe what it is and you get a limit quotient definition, and then you learn some tricks for how to compute them and you never go back to the limit quotient definition again. And we're going to do basically the same thing in this course. So the partial derivative of f answers the question of how fast f is changing as you go in a direction parallel to the axes. So let me draw a little sketch of my favorite function here. This is a good one for illustrating, I think. And so this is f of xy given by 4 minus x squared minus y squared. So here's the xy plane right here. This is z equals 0. And there's the x-axis and there's the y-axis. And here is f coming up this way. And so from this equation right here, if we think of this, the vertical value as being z, then you recognize x squared plus y squared plus z equals 4 as being the equation for a downward opening paraboloid based on your experiences with section 13.6. Okay, so now the idea here, if we say how fast is f changing at the point 2, 1? Okay, well, if we're moving in a direction parallel to the x-axis, so let's actually, you know what, I'm gonna, not so happy with my sketch there. I'm gonna draw it bigger. There we go. And so let's see, so here's my x-axis. Here's my y-axis. And so I'm going to go, let's see, to the point. So there's 2 out here, so just outside the dome, somewhere right around here. Oh, I guess actually it would be more here. And so this is the point 2, 1 that I'm interested in. And then we're looking at the change as we move parallel to the x-axis. So that's in this direction right here. So in other words, we're holding y fixed. And here you see that y is equal to 1. And this line is in fact the line y equals 1. So we're moving back and forth on that line. And so then that means if we look at the trace, so we've got this trace coming through right here. It's going to look like a downward opening parabola. Okay, so and maybe I should continue it on down further a little bit, because what we're going to be doing is we're actually going to be looking at the rate of change of f at this point, which is going to be, oh man, I drew it so it came out super steep, but it's going to be the slope of this tangent line to the blue curve right here. And so the slope of that is denoted as partial derivative of f with respect to x. So how fast f is changing as we move in the x direction at the point 2, 1. All right. And so this is the same thing as g prime at 2 for the function where g of x is f of x, f of x comma 1. And f of x comma 1 is exactly this blue curve right here, right? We've fixed the y variable by constraining it equal to 1, and we're just allowing x to vary back and forth. So my key point in introducing this g here is just, I just wanted to kind of emphasize the fact that this is a function of a single variable. So by restricting y to be some fixed number, we are back in the case of single variable calculus, and you know what this is. This is just a good old single variable derivative from Calc 1. Okay, so if we use what we know about single variable calculus, g prime of 2 is going to be the limit as t goes to 0 of g of 2 plus t minus g of 2 over t. So there's the familiar limit quotient definition from single variable calculus. And so if I write that back in terms of f, then this is going to be f of 2 plus t comma 1 minus f of 2, 1 all over t. Or if you like, we can write this as the limit as t goes to 0 as of f as we move along a curve. Where c is the curve 2 plus t comma 1. So in particular, we pass through the point 2, 1 when t is equal to 0. Yeah, and so now all of a sudden this is starting to look very much like a limit in a direction parallel to the axes, the way that I explained it in the previous clip, where we were just looking at limits and not derivatives yet. But this is the same idea applied to the limit quotient definition. So over here, our curve C is exactly this line parallel to the axis here. So this is C of t, and C of 0 is that point that we're interested in right there. Okay, and so now notice that this entire thing would go through just exactly the same if we had fixed any other value of y. So instead of, so if we were to change 2, 1 to b, actually, you know what, to ab, any other random point, then how would things alter? Well, we would have g prime at a, and then we'd have a, b, and then the rest would be this, oh, down here, a, b, in our definition of C. Okay. So the key point then is that the derivative of f at the point AB, and sometimes, sorry, partial derivative, and the partial derivative is also sometimes written with a subscript, like so. This is the limit as t goes to 0 of f of a plus t b minus f of ab all over t. And so that's the change in the direction parallel to x. And then we have the same thing for the direction parallel to y, if we wanted to do that one instead. So the notation just replaces x by y. And in the definition of the value, it would be a, and now we perturb the second slot by b. And so this corresponds to moving in a direction now that's parallel to the y-axis. So this would be, let me pick a better color here. How about, let's do orange. So we'd be moving now parallel to the y-axis. So we take this for our new curve c. So we're traveling now along. Sorry, that's x. X equals 2. That's why that's being fixed. So we would use c of t is equal to 2 comma t plus 1, or 1 plus t. And this would be slicing. So if we look at the trace on our parabola, we would have some curve that looks like, well, that was a bit wonky, but yeah, something like that.